In other words, now we're gonna do sufficient condition. So it's like continuity is sufficient for integrability. And monotonicity is sufficient for integrability. That's why I would like to prove that, sometimes it's still pretty much difficult to compute lower and upper Riemanns and integrals. But if you only know that the function is continuous, it's sufficient for integrability. And if you know the monotonicity function on the interval, that's sufficient for integrability. So now we're going to do some of the sufficient conditions for this was necessary sufficient. Now we're going to do some sufficient conditions or RS integrability. Okay. And the first sufficient condition is this. So if f is continuous on A to B, then f belongs to the calligraphic alpha of. In other words, it's intangible. So continuity implies integrability. So when you are doing probability theory, so you had what do you call the CDF of normal distribution function? What was CDF of normal distribution?
Integral.
The standard norm e to the minus x squared by 2 over square root of 2 pi and dx from minus infinity x 2 and dt. We can't solve this integrally, can we? But we know for sure that this exists. Why does this exist? Yes. We know that this has the result which is guaranteeing basically that this exists. So we are
unable to find, but it exists.
Yeah, it exists. I mean, if it exists and we are not able to find analytically, then we have numerical methods which can do the job for us. All right, so let's move ahead. So continuity is something easy to verify, but it's a stronger condition. Pretty strong condition. While you can have integrable functions which are not continuous. You can have integrable functions. In fact, we're going to prove that if a function has roughly finite number of discontinuities,
We can remove them.
you can somehow integrate it. Anyway, so let's just think about first that why the continuous function must be integrable. And our way is going to verify this condition. We're going to say that for any partition P,
There exists.
an epsilon positive, this sum can be controlled by epsilon.
For any P, T exists.
No, for any partition. So in other words, for every so for every epsilon positive, there exists a partition. So our task is to find that partition. So given epsilon positive, okay.
Yes.
Choose theta. Choose theta in such a way that it has some distinct properties. Okay? I choose theta such that alpha of E minus alpha of A. Okay, interestingly, there is no condition on alpha. It is true for all monotonic functions. So there is no restriction on alpha. This is something which is choose epsilon positive such that this guy, that alpha as endpoint, is smaller than epsilon by eta. Okay. Eta is something that we have to choose in such a way that this guy multiplied by eta is smaller than epsilon. We can do it. Why we can do it? Huh? When eta of x must be positive. Why we are able to choose such an eta? Just think about it. Alpha is monotonic and bounded. Okay? So if it is monotonic and bounded, so their difference can be controlled by a number. Okay? Then I can relate that number with epsilon by cleverly multiplying or choosing this eta. So I can choose this eta in such a way that this difference is smaller than epsilon by eta. Okay? So imagine this difference is smaller than some m. Okay, so I want to make this smaller than epsilon by eta. So what should I do?
Then epsilon by m or eta.
So you can do it actually. Just think about it. So that's part. So eta, we can always find such an eta information. Now f is now as since f is uniformly continuous. Why it is uniformly continuous? Well, assumption says that it is continuous. Think that we have some result which can guarantee this for us that no, all functions are. We did one example. We said this 1 over x is continuous over 0 to infinity, but it's not uniformly continuous. Do we have any result? So we know that compactness, is actually proved a result at the end of the limits chapter that if you have a continuous function defined on a compact set, then it must be uniform. So it's like we know that uniformly continuous functions are continuous, but when the converse is true, the converse is going to be true if the domain of the function is compact. So is the domain of function compact? It is compact, so it must be uniformly continuous. So if it is uniformly continuous, so there like this, I can choose a delta such that f of x minus f of t is less than epsilon whenever what happens? Whenever x minus t is Yes, X minus T can be controlled by X minus T. So that was the definition is of uniform continuity, and this is true for all x and p in the interval a to b. So what we said we have an epsilon, and since this guy is bounded, then I can cleverly choose eta in such a way that this guy is smaller than eta or epsilon or beta. And since f is uniformly continuous, y continuous, you can mention this that okay, just continuous and with compact hormones, so it must be uniformly continuous. So for this epsilon, I can find a delta such that if the difference of these two is smaller than epsilon, is going to be smaller than epsilon whenever x minus t is smaller than delta. So where we are heading at? We are heading towards some given state. Okay. Where do we have this confusion? Now, consider a partition. Consider a partition. So our job was what? Our job was to find a partition such that the difference of upper and lower Riemann sum should be smaller than epsilon. So consider a partition P, which comprises of x naught, x1, and obviously such that this guy is A and this guy is B of a B such that, okay, there is a restriction, and that restriction is that the difference of all of these xi's is always smaller than this delta. The delta you have. So my claim is that this partition is going to be work. Okay. This partition is going to be for all I equal to 1. Agree? So that's what.
Yes.
Alright, so another thing basically that we can deduce from this previous conclusion, that since f is uniformly continuous or will be continuous on a compact set, so it must achieve supremum and infimum. It is going to achieve supremum and infimum.
By EVT.
Huh?
Extreme value.
Yeah. So by extreme value theorem, there exists S and T such that S and P such that in each such interval Si and Pi such that Mi, which is the supremum of f of x when x is between xi minus 1 psi small mi is the infimum of f of x such that x is between xi minus 1 and xi, okay? And the difference of this mi and, okay, and obviously these SIs and TIs are what we get. So it is going to be equal to what? So I can achieve this supremum and infimum on each subinterval by some instant Si and Ti within that interval. Okay. And if this is the case, then from this inequality that f of x minus f of t, okay. Now, what would be the good thing about Si and Ti? Just think about it. Can I say that the difference between Si and Ti is smaller than delta?
Implies.
If this is the case, why this should be smaller than delta? Because Si and Ti, I'm writing explicitly, are two constants in the xi and xi minus 1. And I know that the difference of xi and xi minus 1 is smaller than delta. So if you take any 2 points between this interval, their distance is still going to be smaller than delta. Okay? So if this is the case, then what does this is going to imply? This is going to imply
Uniform fertility.
that actually mi, okay,
Minus small.
minus small mi is going to be less than epsilon. Agree? Why? Because capital Mi is what? Is f of Si. Ti is what? It's f of Mi is what? F of Ti. So by uniform continuity, you're going to have this answer. Okay. So if this is the case, then I can play around with this inequality and think that I can play around with this inequality in that, okay, multiply this inequality by delta alpha I. So if I have mi delta alpha I minus small mi multiplied by delta alpha I, this is less than epsilon by delta alpha I. Agree? So I can multiply with both, and then I can take sum actually. Okay? I can
Translation.
take sum. I equal to 1 to n, and I equal to 1 to n, and I. Great. I have this person.
Sure.
Okay. Now, if this is the case, then explicitly here that this is smaller than sum of I equal to 1 to n capital Mi minus small mi multiplied by
Epsilon.
this is smaller than epsilon times delta alpha I. Agree? Not equal to but less than. Now this guy is equal to what? So I can take this alpha I outside. So what is going to remain inside?
Epsilon outside.
So I can take epsilon outside. So what is going to remain inside? So it's going to be some delta alpha I. So it's equal to what? So that is a telescopic sum actually. All terms will be cancelled except first and last. Just think about it. So delta alpha 1 plus delta alpha 2 plus delta alpha n and delta alpha n is alpha 1 minus alpha naught and delta alpha 2 is alpha 2 minus alpha 1. So this guy is going to be equal to alpha of b minus alpha of
A.
a. And if this is the case, then what?
Is equal to that.
So this is say smaller than or that. This one, we've done a mistake. Have done a mistake. The little mistake is this, that we can choose even for this eta, I can have a diagram. Even for this eta, I can have a delta. Why this would be the case?
Epsilon is equal to beta.
So,
For this case, we can
yes, take epsilon equal. So it's like since f is uniformly continuous, so for every epsilon, in other words, for every number, you can find a delta. So in particular, I can take that, for theta actually. So this replace the theta by epsilon here. So this will be the case where you're going to have theta. You're going to have theta. And this guy is smaller than theta times epsilon by beta is epsilon. Okay? Now, just think about it. What this guy? So this is your UFP alpha. See?
Yes.
That's what the definition of upper Riemann-Stieltjes, Riemann-Stieltjes. Alpha. So this one. Okay. Is it making sense? Yeah. So the partition that we choose was that the difference should be controlled by the delta. And delta was what? Delta is basically that number which exists
For the
for choice of theta actually. Okay. What we just saw is that for every continuous function, it is Riemann-Stieltjes. It is integrable in Riemann-Stieltjes sense, and hence at Riemann sense. Okay. Here is the but that audience will see video that we made achieve here. Replace epsilon by eta. F is uniformly continuous, so for every epsilon, a delta exists. So in particular, for eta, a delta exists. Say that okay, this delta and eta are basically the helpful things for doing our problem. Okay. Put it off. So what does this result shows that if this is the space of, so it's like if this is calligraphic R of alpha, then the space of continuous function is sitting inside that. It's like that set of all continuous functions on A2. All continuous functions. So sometimes you denote it by CAD, it's like a set of all continuous functions defined on A2. Okay, so CAD is a part of this R of alpha. Okay. So you can have functions which are integrable but not continuous. So you are going to spot another space within that is which may be continuous, which can be decided. You can have continuous and monotonic functions. There is no trouble. Okay. Let's talk about the other class of functions. Let's see. picture is a bit misleading. I'll tell you why. Because CAD is contained in R alpha for any alpha, while the result that I'm going to prove is not true for all alpha. It's true for, so there is a restriction on alpha. So here's the theorem. So if F is monotonic, if F is monotonic and on A to B, and alpha is continuous. That's it. That's a restriction. Alpha is not only continuous, also obviously monotonic. So if alpha is continuous, then F belongs to alpha. We need to keep one thing in hand, that alpha, so we are not only assuming that alpha is continuous, there is also monotonicity also. So we are additionally assuming that if alpha is monotonic and continuous, then the monotonic functions, are integrable with respect to such an argument. Okay. So this picture.
स्टेटमेंट उसने मेंशन भी नहीं किया कि अल्फा मस्ट बी
हाँ?
स्टेटमेंट में उसने मेंशन नहीं किया कि अल्फा मस्ट बी
But like this is implicitly inside the result. Why? Because if alpha is not monotonic, then Riemann-Stieltjes integral does not make sense in the first place. Okay? So if you want to talk about integrability, you need to have monotonicity. You can't have otherwise. Okay, so this picture will be true if you additionally assume that alpha is continuous. Otherwise, it's being anyway, so this is also something. Here's a proof. So what are we saying? Alpha is monotonic and continuous, and F is a monotonic function on the interval A to B, then it is sufficient for proven integrability. Okay. And again, the argument is going to be similar, that we want to show that for epsilon positive, I can find a partition such that the difference of upper Riemann sum and lower Riemann sum is okay. So I will assume without loss of generality that F is monotonically increasing F. Okay. Monotonically increasing. In other words, a similar argument is also going to work if the function is monotonically increasing.
So what is monotonically increasing?
Okay. So by monotonically increasing, I mean, for any two instant S comma T in the interval A to B such that if S is smaller than or equal to T, it implies that f of S is smaller than or equal to T. It's increasing function.
Increasing should be increasing.
Monotonicity is like, okay, it doesn't change the behavior overall in the interval. It's monotone, either increasing and increasing and increasing, not decreasing and decreasing and decreasing. In that sense, it's working. So without loss of generality, assume that F is monotonically increasing, and imagine that an epsilon has been given to you. Okay? My task is to basically think about this. Now, my claim is consider this partition. You're gonna see this again and again when you